Hello, we are BASCO Makes, and we're here to introduce you to the BASCO Isolated Valve Observational Tool System, or the BIVOT system. I'm the project manager, Stephen Behringer.
I'm the systems integrator, Aswan Anbarasan.
I'm the software engineer, Max Surrey.
I'm the hardware engineer, Kyle Condina.
And I'm the network engineer, Emmanuel Ochoa.
Oil platforms and other industrial environments have thousands of valves controlling the flow of high pressure and or caustic fluids. Older valves have no feedback on their position, whether they're open or closed. Issues also include current retrofitting options lacking durability and ease of use, high cost of installation of cabling, hazardous environmental ratings required for an explosive environment. Integrated systems are currently implemented to give positioning data back to a central hub for valve monitoring. If such systems are desired afterwards, the valve must be isolated from the system, shutting down the production for hours or days at a time. By providing an attachable, wireless, easy-to-use sensor, providing near real-time feedback to a centralized hub, we can reduce human error, increase efficiency of changing processes within the installation, give operators better situational awareness of the system, and decrease safety hazards. For example, Sophie's uses a Pepperell Fuse integrated sensor and wired information feedback for positional data. Turk has a 360-degree monitoring system integrated with the motor to fully move the valve. Both these require the inclusion of significant wiring and integration with the valve.
Currently, drilling rigs, oil platforms, and refineries have thousands of valves, most of which provide no status feedback. Because of this, companies implement one of two solutions: to replace the systems with newer systems that provide feedback to control systems, or to send a runner to check the status of the valve. Newer systems often are expensive and require downtime of the facility to install. Sending in a runner introduces human error to the mix as well as human laziness. A worker could check the wrong valve, or the worker could not want to go the distance to the valve. If some personnel doesn't want to go to the valve and tries to assure their higher-ups, bosses, or whatever, that they went to that valve and they know the state of that valve is on or off, given the process going to be done, that could lead to catastrophic failure, cost of human life, and revenue to the company and the industry as a whole. The BIVOT system will utilize a two-part system that will consist of a transmitter that will be attached to every manual valve within the transmission range of each other to create a small mesh network. Also, there will be a receiver that will connect to each mesh network to the control system. The control system will then read and keep track of the status of all the valves in the system.
These are the functional requirements for our project. First, the device must be a non-intrusive modular device able to mount on the surface of multiple types of valves. It cannot require disassembly or machining of any portions of the valve. The device will also be wireless. The device should be able to transmit the state of the valve wirelessly and be able to operate with interference from industrial RF environments. Under normal operating conditions, the device needs to work for approximately 1 year before the battery needs changing or recharging. In prototyping, a commercial battery will be utilized for cost purposes, but a comparable explosive-rated battery will be identified for further levels of production. Next, the sensing methods cannot inhibit the operation of the valve. It must be robust enough to handle harsh industrial use. The housing design of the device at this stage will be made out of 3D printed PLA, but the design choices have to keep in mind not to create issues for explosive rating later in the development process. Lastly, for third-party integration, the output of the receiver needs to be a TCP packet that can be routed over IP to a computer to be integrated with the control system.
And here we have the conceptual block diagram of the BIVOT device. It's going to be part of a mesh network of different BIVOT devices communicating amongst each other to a control center. In the bottom corner, we can see that there's a sensor, and how the sensor would work in concept is you would have the rotating shaft where a magnet would be attached, and it would rotate with the valve and place stationary position around the shaft would be sensors that can measure the change in the electromagnetic field that the magnet creates. And through this, we can measure the rotation of the valve anytime it's turning. So when the sensor detects that it is being turned, an individual sensor would send a RF transmission burst that would either be picked up by the receiver or another transmitter. And if it's another transmitter, it would pass through this mesh radio frequency network until it reaches the receiver, where upon then the receiver would send it back to the control room.
We have the performance specifications. Some of the hardware used include Digi-XB3 microcontroller and the Digi-XB gateway, and magnetic sensors. On the software side, we will be using MicroPython to program the microcontroller.
Here we have the functional block diagram. It is listed as 3 transmitters. The one on the left side is the fully broken out transmitter to show you the functional block diagram, and the other 2 are to demonstrate the mesh networking capabilities. The red lines are going to be the power inputs to the XB3. We're going to be powering this with a CR2032. That is a commercial battery and is not explosive rated. One of our deliverables will be to provide an explosive rated comparable battery for final production. In prototyping, we'll be using off-the-shelf for cost purposes. The power comes off of the CR2032 and goes into pin 1, which is the voltage pin of the XB3. From there, it also branches off to the 4 magnetic sensors, the S17221s, that we'll be utilizing to measure the magnetic field off of the magnet attached to the rotating portion of the valve stem. Additionally, there is a reset button that will be attached to pin 10. This is designated as the reset pin of the XB3. Pin 10 on the XB is the ground pin for the microcontroller, which will also be a common ground to all the magnetic sensors. The blue lines coming off of the XB to the magnetic sensors will be an analog input read out of the magnetic sensor of any magnetic fields that they sense and can be read by the microcontroller. The narrow black lines on the right side of the XB3 are going to be binary 1s and 0s to control a MUX. The larger black line at the bottom right of the XB is the wireless antenna coax cable that goes out to the transmitter that will transmit to the other transmitters and or receiver to get the RF transmission of its state to the control system. The mesh network is denoted by the dashed yellow lines between all of the transmitters and the receiver. Any node can transmit to another node or the receiver. So as long as the receiver can transmit to at least one node and that node can transmit to another node, the far node, even though can't reach the transmitter, can transmit to the nearer node and essentially leapfrog its way back to the receiver, which then will transmit via the blue line off of the XB gateway, which is its own isolated device, and transmit that information via Ethernet cable as a TCP packet to the control system. The XB will use the data lines off of the magnetic sensors to sense where the magnet is positioned on the valve. It will check this every 30 minutes and then go into sleep mode. So when it is in sleep mode, we can utilize less battery so that we can extend the battery life and push this out as far as we can, hopefully utilizing about a year worth of service life under normal conditions out of a single battery. The data lines going to the MUX will be setting what the MUX will watch for. So whenever a valve is set to a position, a certain sensor will be on because the magnet will be next to it. We will set the MUX to watch that and wait for its state change while the microcontroller can go to sleep, so utilizing less battery power. Once the state changes of the magnetic sensor, it will send the signal to the MUX, which will then wake back up the XB so that it can go back to processing and checking what the state is and can go into checking whether or not it is on or off or in motion and count the rotations of the device. Next, we'll be going over scheduling, starting with the work breakdown schedule, then the responsibility assignment matrix, followed by the Gantt chart, and finishing with the network logic diagram.
Here we have the work breakdown structure for the sensing unit on our BASCO system. Starting by familiarizing ourselves with the valves and their methods of operation, size, and specific dimensions, we were able to quickly move from there to concurrently conceptualize our designs for our 90-degree turn valves and our multi-turn valves. Once our design was selected, we were able to pick the specific individual component parts that would allow us to follow through with our desired process. With both a conceptual design and a functional design already built, our next step towards building our sensor is an Altium schematic to work on the minutiae of the design. Once that is complete, all that will be required is a physical build of the circuit and sensor. Once physically built, the system will need to be extensively tested to ensure all functionality requirements are met.
Here we have the work breakdown structure for the communication nodes, which I am in charge of. The main goal of this node is to facilitate communication between the receiver and the transmitter in order to build a RF radio frequency mesh network that will allow the data to be sent to a control room. We start by studying RF transmission methods and what components can be used to achieve our goal. We then create a transmitter and receiver design based on this information. Once we have all the components we need, the next step is try to make a bare bones transmitter and try to have them communicate. From there, we implement a program that will allow for the creation of a mesh network. Once this has all been tested and verified, we implement into our final design.
Here we show the work breakdown structure for the networking node. The goal here is to bring things together to complete the network connections. That way data can be sent. To start, we test the receivers to make sure the connections are present. Once this is established, we move on to specify our network protocol. In our case, we will be using Zigbee, which is based off the IEEE 802.15.4 standard. To finish this off, a design for the network integration for the receiver will be made.
Here we have the work breakdown structure for the power unit. Once the design and the components are finalized, we will estimate the power consumption of the device and the required battery capacity. Then we'll move to finding batteries that are suited to be used in a potentially explosive and hazardous environment. And finally, we'll select the batteries that satisfy our technical requirements. Here we show the work breakdown structure for the orders. I'll be in charge of ordering our hardware necessary for completing the project.
As the project manager, I'm in charge of the 6.0 management node, which includes weekly risk management, meeting scheduling, third-party coordination, Fisher Design Center coordination, as well as coordinating project deliverables being turned in, and all academic coursework.
As you can see, the designs were of critical importance to finish on time, incentivizing us to quickly get them done. The Altium schematic has a similar importance to the overall timeline. I have the same person for secondary on all my assignments except for the proof of concept build and where the entire team is a secondary.
And here we have the responsibility assignment matrix where it shows that I am mostly in charge for all Node 2 communication modules and packets. And it shows my secondary who would share my responsibility in all the deliverables. And as we can see here, the transmitter and receiver design are a high risk critical importance to be delivered.
This is a responsibility assignment matrix for the networking, power, and parts list portion of the project with its associated secondarily responsible person and the associated risk level.
Here we have the responsibility assignment matrix for all the 6.0 portions. As the project manager, I'm in charge of most of these and have secondary personnel assigned as needed. They are also listed by their risk level. So certain deliverables that are of a higher priority, both in grade and in timing, have a higher priority than other assignments.
The Gantt chart for the BASCO system is displayed here. We have the majority of our tasks built for this semester, leaving second semester for significant time to test and, if necessary, rebuild parts of our system. We are currently working with unknown deadlines for our second semester and have reflected that in the black bar at the bottom of the Gantt chart. We are currently comfortably on time with the tasks we have set for us, only meeting resistance or delays in tasks that we have expected, where we gave ourselves ample time for adjustments.
Here we have our network diagram, which breaks down our schedule for all of our activities needed to complete the capstone project. On the bottom, we start off with the transceiver and receiver designs. We study and look into RF transmission. We come up with a conceptual design, then a functional design. Eventually, we begin ordering parts and manufacture the transmitter and the receiver, which we would later use to communicate with each other. Then we would go into programming for these devices, creating a mesh network that would allow us to send data across the network to a final receiver. The middle line indicates our research and development into choosing a battery for the device. It is the path with the most slack, allowing us for the most time to explore our options when it comes to batteries, especially when it comes to ones rated for hazardous, explosive environments. The top line is a chain of events and goals that we have to meet in order to develop a sensing unit for the device. We start off by looking into possible methods for sensing on the device. We create a conceptual diagram, then a functional diagram, then begin to order parts, then end up manufacturing the device, testing it, mounting it, And then all these chains come together at the end to create the BIVOT device, which we end in testing.
Shown here are the project assumptions. Our first assumption is that all parts needed will be available to complete the project. Parts will be needed to be ordered far in advance so that the parts are received before the due dates. The next assumption is that the project timeline will not be delayed due to external factors such as COVID. Another assumption is the Wi-Fi integration for transmission of the valve state. We need to make sure that the transmission internal to the system can overcome the RF environment of the oil rig and the control unit can utilize the TCP information into its software. The last assumption is that the expenses will not go over our allocated budget. This means that parts and shipping costs do not increase from the current estimates. The BIVOT system will save time and money for any company that implements it on their valves. The current method for checking valve orientation is to send a runner to physically check the valve. Such a process takes time, is susceptible to human error and negligence, both of which can cost money and create unsafe working environments. With the BIVOT system, this positioning of the valve can be checked from anywhere with an internet connection, eliminating the need for a runner. This will increase efficiency of changing processes at installation, give operators better situational awareness for the state of the system, increase efficiency of the operation, and decrease safety hazards. With integration of this system, there will be mitigated human error with an increase in productivity in the petroleum field.
Current solutions of valve positioning sensing are too expensive and cumbersome. They create human errors that can be avoided or have prohibitive costs in time, installation, and man-hours. BASCO Makes proposes the implementation of the BIVOT system on manual valves that do not provide feedback to any control system. The BIVOT system will be able to read the orientational positioning of a valve and send that information to a monitoring station, where it can be used in the diagnostics, operation, and maintenance of the facility. The device will be rated for explosives and hazardous environments as a battery-operated unit, which will allow it to run for a year under normal operating conditions. The BIVOT system is a wireless, modular, add-on device that detects the position of a multi-turn or a 90-degree ball valve.
Thank you for watching our presentation on the BASCO Makes BIVOT system. If you have any questions, please direct them to the comment section of the YouTube video, and we will get someone with you shortly to answer your questions.